All right, we just finished talking about vectors. Now we're going to move on to talking about a vector space. So a vector space will seem kind of abstract, but while we're talking about vector space, just think about R2. Remember, what is R2? Well, it's a set of all ordered pairs of real numbers. So you can think about it as a two-dimensional space, right? All vectors with two entries, where those entries are real numbers. That is one particular example of a vector space. And really any dimensional space we can consider a vector space. You can think of it as a space of vectors. But we'll be able to even talk about more than just vectors of numbers. We'll eventually talk about sets of functions. So like the set of all polynomial functions will also be a vector space. But what is a vector space? A vector space is a non-empty set V of objects. So it can't be empty. And we're just using the word objects because we're not going to restrict ourselves to just vectors where those vectors contain numbers like R2. But thinking about R2 in the beginning will be a helpful way to think about a vector space. So we call these vectors on which we're going to find two operations, addition and scalar multiplication. And we've looked at addition and scalar multiplication in the last video, how to add vectors and scale vectors and do both at the same time, which we call linear combinations. All right, we'll keep moving on here. Subject to the 10 properties below. All right, so there's 10 properties listed here, and we'll go through each one using R2 as our particular vector space that we're thinking about. So the properties must hold for all vectors u, v, and w in this vector space V, and for all scalars c and d. And before I go through all of these properties, just keep in mind that if you have a set of objects that satisfies all these 10 properties, then we'll be able to do pretty neat things that we'll see later on in the course. So that's kind of a reason for why we're going through these details, these properties of a set of objects. All right, so let's look at the first property. The sum of the vector u and the vector v is in the vector space. So think about R2. If you add any two vectors, u and v, that live in R2, you would get another vector that lives in R2. So that still is in the vector space V, or the vector space R2, where V is R2. An example of a set of vectors that doesn't satisfy that is if you have a finite set, like maybe you have two vectors, maybe one vector is 1, 1, another vector is 2, 2. You add those two together, you get 3, 3. That new vector, 3, 3, was not in your original set of those two vectors. So that's an example of property 1 not being satisfied. All right, property 2, if you change the order of addition of the two objects, the two vectors, you get the same result. That's all property 2 is saying. So pretty trivial there. Right? So you can think about R2, that's always true. Even that finite set, if you have two vectors, right, that I gave 1, 1, and 2, 2, that does satisfy property 2, but it doesn't satisfy property 1, right? So we have to satisfy all 10 properties here. All right, the next one, right, if you have three vectors and you add u and v together first, or v and w first, and then the remaining one later, doesn't matter which order you add those together. Property 4, there is a zero vector, 0, denoted by the 0, in V such that u plus 0 equals u. Right? So in R2, the 0 vector would be the vector 0, 0. Right? And so R2 satisfies that property, because if you take any vector in R2 and add 0, 0, you still get the same vector that you started with. Property 5, for each vector u in our vector space, there is a vector negative u, right, so scale u by -1, that's in the vector space such that when you add those two together, you get 0. Right? So for example, the vector 3, 3 in R2, we know in R2 there's also -3, -3, and we add those together to get the 0, 0 vector. So R2 definitely satisfies property 5. Property 6, the scalar multiple of u by C, denoted by CU, is in V. Okay, so think about R2. If you take any vector in R2 and scale it, so maybe the vector 10, 7, and you scale it by 100, then you'd get 1,700, right? That's still in R2, so R2 satisfies that property. Another way to say that property is R2 is closed under scalar multiplication, right? You might hear that word closure. Closure just means by scalar multiplication, it means that if you scale a vector in your space, you're still in your space. Property 7, if you scale the sum of two vectors, you can first scale the vectors individually and then add later. Right? So you can think of that as distributing the constant multiple C through to both vectors. Property 8, if you have a sum of two scalars and then you multiply it by the vector u, that's the same thing as first distributing the vector u through, so you get cu plus du, right? That's the same thing. So pretty trivial there. The ninth property, if you first have a scalar multiple d times u and then later scale it by c, that's the same as if you just take your two scalar multiples, multiply it together first, and multiply by your vector v. And lastly, the scalar multiple 1 times u is still u. Right, so that's also a very trivial one. So some sets of vectors satisfy all 10 of these properties. Some sets might not satisfy these properties. And we could come up with examples like I did, where there's sets of vectors or sets of objects that don't satisfy some of these properties. But as I said in the beginning, when sets do satisfy all 10 of these properties, we'll be able to do some pretty cool math, some pretty cool mathematical moves with these sets later on in this course. So that's why we describe all those details first. All right, another term that we'll be using in this course, and not just a term, but a concept, is a subspace. So a subspace is a subset of a vector space that still has all the same properties, those 10 properties of a vector space. We call that a subspace. So if you have some vector space, which right, it's a collection of vectors, a collection of objects, and you take a subset of that collection, and if it still satisfies all those 10 properties, then we call that subset a subspace. All right, let's look at some examples. So here is a subspace of R2, right? We said R2 is a vector space. Now we'll look at some subsets of that vector space. So imagine our plane representing all of R2. If you have a line going through the origin, that line is a subspace. You can go through that list of all those 10 properties, right? This line represents an infinite number of vectors, and you can go through those 10 properties and see if all of them hold. And you'll see they do. Right? A line going through the origin will satisfy all those properties. Just to name a few, if you take any two vectors on this line and add them together, you'll stay on the line. You'll stay in the subspace. If you scale any vector on this line, then it will stay on the line. So we call that closed under addition and then also scalar multiplication. Any vector on this line does have the negative of that vector such that when you add them together, you get 0. Right? So there's 3 properties, and you can go through the rest on your own to make sure all 10 properties are satisfied. All right. There's another line going through the origin. This is also a subspace of R2. So there's 2 examples of subspaces of R2. Something that's not a subspace of R2 would be a line that doesn't go through the origin, right? You can imagine picking 2 vectors on this line and add them together, right? And you'll definitely not get a vector that's still in that line. Right? Even if you add a vector to itself, right, some vector that you choose on this line, if you add it to itself, it won't even be still on that line. right? For example, maybe that there's that vector 0, looks like maybe 1.1 or something like that. So the vector 0, 1.1, if you add that to itself, you get 0, 2.2, and that's definitely not on the line anymore. And also, any scalar multiple of a vector on this line would give you a new vector that's not on this line. So this is not a subspace of R2. Another example would be two lines going through the origin. So you might think this might be a subspace because we already said a line going through the origin is a subspace. But if you have two lines that go through the origin, imagine picking two, one vector on one line and another vector on the other line, add them together, right, using that parallelogram rule, you'll get a vector that's no longer on the line or on either line. So it wouldn't stay in our set of vectors. So that is not a subspace of R2. And a plane that is just in the first quadrant, you could say including the axes, that is not a subspace because, for example, you could take the vector 1, 1 and scale it by any negative number, and you'd no longer be in the first quadrant. Right? If you take the vector 1, 1 and scale it by negative 2, then you have negative 2, negative 2. That's in the third quadrant, which means you're not in the set anymore. So it doesn't satisfy that property of a vector space. Remember, a subspace is just a subset of the vector space that still has all those 10 properties of a vector space. So the first quadrant, including the axes, is not a subspace of R2. Now I focused on the closure of scalar multiplication and addition of vectors to check if they're subspaces. That's usually an easy way to check if something is a subspace, but you can really look at any of the 10 properties when checking to see if something's not a subspace. But to see if something is really subspace, you have to verify all 10. To show that's not a subspace, you can just find one property. A lot of times the closure of scalar multiplication additions are good first ones to check. But that's a way to show that something's not a subspace, is just find one property that's not satisfied. All right, so we've gone through these abstract concepts of vector space and subspace. Now let's just summarize some of our conclusions. So any dimensional space, that is Rn, so where n is any positive integer, so not just R2 and R3, but really any dimensional space, that is a vector space. It'll satisfy all those 10 properties that we looked at. Now for subspaces, a line through the origin in that n-dimensional space is a subspace of Rn, right? Because a line would be a subset of some n-dimensional space. And as long as it goes through the origin, it will satisfy all those 10 properties. Likewise, a plane going through the origin in Rn, as long as n is greater than 2, so they can actually have a plane being a subset of the n-dimensional space. A plane through the origin is a subspace, so it will satisfy all those 10 properties and be a subset of that vector space Rn. And you can kind of think through those 10 properties, and with a plane going through the origin, it'll be just like a line going through the origin, right? Any vectors that you choose in the plane, add them together, they'll stay in the plane. Any scalar multiple of the vector in the plane will stay in the plane. If you pick any vector in that plane that goes through the origin, there'll exist a negative of that vector, such that when you add them together, you get 0 vector. So those are 3 of the properties, and you can think about all the other 7 properties for a plane going through the origin, right, and show that it is a subspace of Rn. All right, another term and idea that we need to think about is this idea of span. So what does span mean? Well, the definition is you have a set of vectors, v1, v2, all the way to vn. So you have n vectors. So if n was 10, then you have 10 vectors. That set of vectors spans a vector space v if every vector v in this space can be expressed as a linear combination of them, right? So we've talked about linear combination. It means scale and add up the vectors that you're working with. So if v, any v in your space, any vector v in your vector space can be written as a scalar multiplication and addition of your vectors, then we say that those vectors span your whole vector space, right? Nothing is left out. There's no vectors in your vector space that are left out when you scale and add up all the vectors you're considering, right? So if those vectors that you're considering span the space, then it gives you everything in that vector space. So one example is like if you have R2, that's your vector space. All you need is two vectors, right? Maybe the vector 1, 0, another vector is 0, 1, right? Those two vectors, if you scale and add them all up, are all linear combinations of those two vectors. You could get any vector you'd like in R2, right? If you want the vector 5, 7, then do 5 times the first vector plus 7 times the second vector. That's an easy example to think about. But we'll have to think about more complicated examples. So if you have these three vectors, 1, 0, 0, 5, and 2, 3, right, these vectors do span R2. Now, how do I know? Well, think about scaling and adding up those three vectors. Can you get any arbitrary vector in R2? That's a way to think about it. Well, if you're scaling and adding up those vectors, you can write that as a system of equations, right? C1 times 1, 0, C2 times the 0, 5, C3 times the 2, 3. We're saying that equal to AB, so we can scale the first entries, the first elements, and add them together to get that first equation, and scale the second elements by C1, C2, and C3, and add them up to get the number B, and check to see, does this system have a solution? Well, you write your augmented matrix, and we realize this system has actually an infinite number of solutions. So you're definitely always going to have a solution, right? You never have a contradiction. So using these three vectors, you can produce all vectors in R2, right? Because our augmented matrix here shows that there does exist a solution for any A, B, right? You'll never get a contradiction. Remember, we get the contradiction when we have a row in our augmented matrix where we have like a bunch of zeros, then the last column has a non-zero number, right? Because that'd be a contradiction. Say 0C1 plus 0C2 plus all the way to 0Cn equals a non-zero number. Right? That's a contradiction. But you don't get a contradiction in this case. Right? All right, example of a set of vectors that does not span R2 would be these two vectors, 1, 0, and 3, 0. Right? Because think about scaling and adding up those two vectors. Can you find some C1 and C2 such that you get an arbitrary vector AB in my space R2? Well, we can do the same thing, right? Scale the first elements. So C1 times 1 plus C2 times 3 equaling A, right? So add the first entries and the corresponding entries in sum equal to A. And likewise for the second elements in each vector, right? As you have 0C1 plus 0C2 equaling B. Now, does that have a solution for all A and B? Well, we write our augmented matrix. We really didn't have to in this case because you could have just seen it from your system of equations. But that second equation, or the second row in the augmented matrix, shows that there is a contradiction. So there's no solution for some A and B in R2. Right? In particular, whenever B is non-zero, then there's a contradiction in our system, which means there's no C1 and C2. Right? You can't scale and add up our two vectors in our set to give you that vector AB. So in the end, we can say the vectors 1, 0 and 3, 0 do not span the vector space R2. All right, the last idea and term to be introduced in this video is this idea of linear independence. So what does linear independence mean? It's this, if you have a set of vectors, v1, v2, all the way vn again, they are linearly independent if the linear combination of those vectors equaling 0 is true only for C1 equals 0, C2 equals 0, Cn equaling 0. So if all the constant multiples are 0, and that's the only solution to that equation, then we call those vectors linearly independent. If there are non-zero values for C1, C2, all the way to Cn that make it true, then the set of vectors are called linearly dependent. So if there's some non-zero constant multiple, such that when you do the linear combination of your vectors that you're considering, and if that equals 0, when you have a non-zero constant multiple, then those vectors are dependent. All right, let's look at an example, because that is kind of a complicated definition there. So this set of vectors, these two vectors, are linearly independent. Now, why is that the case? Well, let's go straight to the definition. If we do the linear combination of those two vectors and set it equal to the 0 vector, all we're wondering is the only solution to this equation C1 equals 0 and C2 equals 0? Right? Or is there some non-zero scalar multiples that make this true? And if that's the case, then it's linearly dependent. So we can scale the first entries and add them up and set equal to 0, and scale the second entries, add them up, and we get this system of equations. And we see, we can write the augmented matrix, and we see the only solution to this system is if C1 is 0 and C2 is equal to 0. There's not more than that solution. There's not an infinite number of solutions. There's just one solution to this system. So only solution is C1 equaling 0 and C2 equal to 0. Example of a set of vectors that's not linearly independent are these three vectors. Well, why is that? Well, if you look at the linear combination of those three vectors and set it equal to 0, 0, right? We're checking to see if there's just one solution to this equation. That is the what we could call the trivial solution when C1, C2, and C3 are all 0. Well, you get the system of equations here. You could write the augmented matrix. And we can see right away that there's an infinite number of solutions to the system. Right? We can write C1 in terms of C3, and we can write C2 in terms of C3. Right? So the 0 solution and the 0 vector is not the only solution to this equation. So there's infinitely many solutions. That means there's infinitely many solutions. That means these vectors are linearly dependent. It's not independent. Now, a more intuitive way to think about this, especially for this not independent case, is since they're not independent, that means you can have some solution, C1, C2, C3, where those are non-zero. And that means you can rearrange the equation to write one vector in terms of others. So you can have one vector depend on the combination of the other vectors. So maybe that makes more sense with this independent and dependent language. When they're independent, that means C1 and C2 equaling 0 is the only solution. That means you can't rearrange the equation to have one of the vectors expressed as a combination of the other vectors, right? So when C1, C2, and all the other constant multiples are 0, you can't rearrange the equation to solve for one vector in terms of the other. So that means they're independent because you can't write a vector as depending on the others. So hopefully that gives a more intuitive idea on why we're calling it independent and dependent. Okay, so this video was a bit more abstract than we're used to. So far in this course, we've covered vector spaces, subspaces, what it means for a set of vectors to span a vector space, and for a set of vectors to be linearly independent or dependent. All right, so get some practice on those, and definitely let me know if you have any questions on any of that. Thank you.